All right, for today, we're going to be looking at cases of static equilibrium. We already talked about torque, but static equilibrium is cases where things are not moving. So equilibrium, we learned in the first semester, we said that equilibrium is when the net force is, net force is always equal to m, when the net force is equal to 0. And that was for point masses. So now, when we're dealing with objects that are not point masses, equilibrium means both the net force is 0 and net torque is 0. And then static means not moving, so static equilibrium is referring to objects that are not moving at all, objects or systems. Right? So in some cases we'll just write net torque equals 0. In some cases we'll have to write both and have two unknowns and solve and so forth. And a reminder, the gravitational force acts at an object's center of mass. Well, really it's acting all along the length, but we treat the gravitational force as though it is acting at the object's center of mass. So that's all I have to instruct you in principle, but and then just work through various examples of this. And this isn't easy or trivial. It's tricky to work through these. We'll figure it out. So let's look at this. A uniform rod is hung from a string. A rod, string is hanging from its center. The mass m is hung a distance L to the left of the string, where should an additional mass of 2m be hung in order for the rod to balance. So balance means, stay chilling out there. And when an object is balanced, then the net torque will be 0 around an axis of rotation. Another way of saying that is that the center of mass has to be over the support point. But yeah, so if the string is at the center, we've got another mass. Well, it's fairly obvious that the 2m should be over here on the other side of the support, because otherwise it would exert a torque in the same direction as this mass, and the rod would rotate. And then we want to figure out what this distance is going to be. Well, in any of these problems, we need to pick an axis of rotation. Now, we're not told the mass of this rod, but the gravitational force on the rod will act at the center of mass. We also have a support force from this string acting at the center of mass. So if we choose our axis of rotation at the center of the rod, then we can write a torque equation, and both of those forces will not be a part of it because they are acting at that point. So the distance from the axis of rotation is 0, and so then the torque from those forces is going to be 0. You can get the correct answer to one of these problems by setting your axis of rotation anywhere. However, you can make your life a lot easier if you set your axis of rotation at points where unknown forces are acting. So then we can write net torque equals 0, and we've got a torque from this guy. Force is mg, distance is L. It's acting at 90 degrees to our radius vector, so sine of 90 is 1, so we just have a torque of mgl, and that's going to act out of the page, so we can call that the positive direction. Then in the opposite direction, we've got a 2mg times x, and those add up to 0, and doing some simple algebra shows us that x is going to be L over 2, which is probably what you might have intuitively figured out anyway, since it's double the mass, it needs to be half the distance. So there's one example. Next up, the uniform diving board of length L is anchored to supports at one end and a distance L over 3 from the same end. So we've got diving board, and we've got a support at one end, and then the other one is L over 3 from that end. Diving board has length L. Mass of the diving board is M. Find the force exerted on the diving board at each point where it is attached to the supports. So we know that we have a gravitational force acting halfway down the board, right? And then we know that these supports are going to exert forces at these 2 points. Now, you may not know what direction those forces are acting. In principle, if it's an unknown force, you don't know what direction it's acting. But you can just pick a direction, and then if it turns out it's the opposite direction, it'll just come out to be negative, and you'll know that you picked the wrong direction. But you can still give the correct answer at the end. So I'll just assume these are upward. I'll call them N1, N2. They're sort of normal type forces. And we'll go from there. Now, we can pick our pivot to be wherever we want it to be. So I will choose the location of one of the unknown forces so that I can write an equation that only has one unknown. So I'll choose the end over here to be my point, and then we're saying that torque equals 0. So we have N2 times L over 3. That's acting out of the page. Gravity is going to be acting into the page. The torque will be into the page, and that's a distance L over 2 away from the pivot. Both of those are perpendicular to the board, so that those then add up to 0. And we can solve for N2. L's cancel out. Multiply by 3. We get that N2 equals 3/2 mg. It came out positive, so that is upward. Then we need a second equation to solve for N1. There are 2 different ways we can write a second equation. You can write a torque equation with the pivot point here, or you can write a force equation, which is what I tend to do because it's a little bit easier. It doesn't require you to think as much. I can also write that net force equals 0. So upward, we have N1 and N2 and mg, and they all add up to 0. So 3/2 minus mg gets us 1/2 mg. So N1 is minus 1/2 mg. So that's 1/2 mg down, which might seem kind of weird, but that's actually how it is. This will hold the thing up, but this one is actually pulling it down to keep it from rotating in the direction that the gravitational force would cause it to go. And you kind of know this, or well, you don't know this, but when you're carrying a long, skinny object, you sort of naturally will do this, exert a downward force on the end while you exert an upward force somewhere in the middle to hold it up. Yeah. Next example, got a bridge of mass 1,700 kilograms, length 20 meters, supported by pillars at each end. Pillar, bridge, pillar. Car of mass 2,000 kilograms is 8.5 meters from one end. Car. And determine the force, yeah. So, we got 20 meters, 8.5 meters. I'll say this is N1, N2, mass of bridge times G. Then we've got mass of car times G. Those are all of our forces acting at their points of application. And we can go, again, we have 2 unknowns, so we're going to need 2 equations. I can set my axis right here. And then I have into the page the mass of the bridge times G times half the length of the thing, and that's in the counterclockwise, in the clockwise direction, so negative, minus mass of car G times its distance, which, whatever, I'll say it's X. And then we have a support force from the other one acting a distance L away, 0, and we have numbers for all of these things, so the mass of the bridge is 17,000. half of the distance is 10. Mass of the car, 2,000, 9.8. It's 8.5 meters from that end, which makes it 20 minus 8.5 is 11.5 meters from the other end, plus N2 times 20. And then we can calculate. So we got 17,000 times 9.8 times 10 plus 2,000 times 9.8 times 11.5. If we move them to the right side, they both become positive. So by 20, we've got that the force from the second one is 94570 newtons up. And then for the other one, again, I would write net force equals 0. You can do whatever you want. So you have N1 plus N2, which is 94570, minus bridge mass times G minus car mass times G equals 0. So, oops. Take 94570 minus 17,000 times 9.8 minus 2,000 times 9.8. And that's on the left side, so when we move it over, we get that the other force is positive 91630, which is 91630 newtons upward. This one is also upward.